I'm holding in my hand a piece of a truck axle. This was given to me by a former student a number of years back, and it's quite heavy. It has a mass of around 16 kilograms, and it is made out of a material called chromoly steel. Chromoly is an alloy made out of iron, chromium, molybdenum, and carbon. Turns out that creating a truck axle out of pure iron just wouldn't cut it. It's too soft and susceptible to corrosion. But adding the other elements to it makes it a lot harder and stronger and less susceptible to corrosion, which is what you want in a truck axle. But what are alloys, and what do I need to know about them for the AP exam? Welcome back, everybody. My name is Mr. Rudolph, and today we are talking about AP Chemistry, Section 2.4, the structure of metals and alloys. And in this video, we are going to be looking at the general structure of metals, and then what alloys are, and then two specific types of alloys you need to know about. And then we're going to start looking at some multiple choice and free response questions, including a drawing of this one, and we'll look at some tips for your own drawings on the AP exam. So grab your pen and let's get started. Let's begin with the essential knowledge statements for this section. Metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons, i.e. a sea of electrons. You may have heard that term before. Interstitial alloys, that's a big term, form between atoms of significantly different radii, where the smaller atoms fill the interstitial spaces between the larger atoms, e.g. with steel, in which carbon occupies the interstices in iron. Fancy term. Substitutional alloys form between atoms of comparable radius, where one atom substitutes for the other in the lattice. Now that's big difference, and you'll see it a lot this episode, where we're looking at different radii or similar radii, and that constitutes the way we predict whether something's going to be an interstitial or a substitutional alloy. Now let's look at some background information about metals and how they work. Metallic bonding describes an array of positively charged metal cores. So you'll see diagrams that look like this, where we have the positive cores in a pretty regular arrangement. They actually do use the term crystal structures on these, surrounded by a sea of mobile electrons. Okay, this is what makes metals, because metals, as you recall, have fairly low ionization energies, right? Their electrons are farther from the nucleus, and they're given off really easily. In fact, the metals would rather give them away than keep them. They're very loosely held. And so what happens is an electron can actually jump from one core to another and just move around the solid, because none of the metal cores want to keep track of it. And so the electrons are free to move throughout the sample, which is where we get the term the sea of electrons. Here's another representation of, in this case, iron, and you got the negative charges flowing around, but the positive cores are staying relatively stable. Metallic substances, because of this, are good conductors of heat and electricity, because you got these mobile electrons that can move around and do their thing. They have a wide range of melting points and are shiny, malleable, ductile, and readily alloyed. There's our term for the day, alloyed. Okay, and an alloy is what we get if we start swapping in different metal cores into the crystal that is actually there. So again, here we have the free electrons and the metal ions that are there. Okay, so what is an alloy? Let's get a definition out there. An alloy is a mixture of two or more elements, at least one of which is a metal. And that forms a new substance with desirable properties like increased hardness, strength, or corrosion resistance, like my truck axle here. Alloys are created by melting and mixing the components, often to improve upon the characteristics of the base metal. Common examples include steel, iron and carbon, brass, which is copper and zinc, and sterling silver. And the list goes on and on. There's tons and tons of alloys out there, and there's no limit really to the range of substitutions. Like, they're just mixtures, and so a mixture can occur in any proportion. High amount of iron or low amount of iron, high amount of carbon, low amount of carbon, and each one has its own unique properties. Those two terms we saw in the learning statements are substitutional or interstitial. All right, and look at these diagrams. In a substitutional alloy, Atoms of similar size simply replace atoms of the original metal in the lattice. The resulting alloys usually do not display high degrees of hardness. Okay, so it's kind of like if I have all these blue ions and then I have these yellow ones that are about the same size, they can just kind of pop in there and take the place of one of the blue ones. In an interstitial alloy, atoms of much smaller size are added to the metal. These atoms occupy the interstitial space, that's what we call this thing, between the larger metal atoms and hampers their ability to move past each other and be malleable overall. The result is usually a harder metal sample that resists deformation. So without anything in this interstitial space, these atoms can kind of bump past each other pretty quickly and easily. But those kind of like just make it a little bit harder for these atoms to slide past each other because there's just something more in the way in that space. So key difference between those two. Some alloys, like solder and some other amalgams and things like that, are purposely made with atoms that don't stack together very well at all. And they just kind of, if you were to look at the crystal structure, you would just see kind of this random loosely held group of metal cores, and they might have super softness and low melting points and so on. So not a lot of notes for today, so we're already on to the question portion of the video. So we're going to look at some AP style multiple choice questions, very similar to ones that have been on past exams and things like that. So hopefully you'll see some similarities when you take your exam. Based on the particle level diagram below, which statement best describes the conductivity of the substance? So we have to kind of look at a bunch of diagrams and kind of see what we're supposed to see, I guess. And in this case, I'm seeing a bunch of positive cores and a bunch of free electrons, not negative ions, but just free electrons. So this would make it different from an ionic compound like we saw in past videos. So I'm supposed to recognize this as a metal sample. Okay, and if I know anything about metals, if I've been paying attention in the note-taking section, I know that metals will conduct electricity. So I'm looking for conductivity. It will conduct electricity, but why? It will conduct electricity because it's a nonmetal, or it will conduct electricity because it has loosely held electrons. And that's really the key that they're asking us in a question like this. So keep that in mind. There's not so many ways that can be asked, so you'll probably see that in maybe a slightly different way here and there. All right, check it out. Here's our sea of electrons. When you see this, you know you're looking at a metal. Here are the ion cores, and you got the negatives in there. The diagram above shows a particle level model of a metallic element. Great, they tell me that. This element would probably be, okay, and then this is all about the properties of metals. Would it be brittle, conductive, or malleable? Well, I know that metals aren't typically brittle, and they do conduct, and they are malleable, so I got to kind of spend some time down here in this little section. Conductive because the protons are free to move around, conductive but only in aqueous solution, and malleable because the electrons are delocalized and can move around. And hopefully your spidey sense is tingling that it is letter D. It is conductive, but not because of the protons. It's because of those electrons. And yes, it is conductive, but it doesn't have to be an aqueous solution like an ionic compound would. You have to get it into solution before it conducts. Metals just conduct because that's what they are able to do with those electrons. And so letter D is our choice there. Okay, quick pause the video about metals and their properties. Take a moment. Again, we see the electron C. And which of the following best describes the properties of the substance depicted in the diagram above? Take a moment, pause the video, and see if you can guess the correct value here. Great, and if you chose letter D again, that it is a metallic solid that would exhibit malleability, then that is correct. It's showing that the ion cores can move past each other if you hammer them or push them or bend them, and that kind of thing. Okay, now we're going to get into alloys. So we get used to seeing diagrams like this. Chromium atoms have a radius of 125 picometers, and zinc atoms have a radius of 133. Which diagram below best represents an alloy of chromium and zinc? Okay, in this case, they're telling us what the radii are, and we have to take that and say, is this going to be, I think it's going to be an alloy, an interstitial alloy like this one, or more of a substitutional alloy like this one. This one right here shows all the same colored circles, so that's not going to be my choice because I actually am going to have two different colored circles. And this one is not my choice because it looks like an ionic compound to me with positive, negative, and so on. So is it interstitial or substitutional? Because these are similar in radius to each other, like the chromium is big enough that it's not going to be able to fit in those little spaces between the zinc. And so we're looking at more like a substitutional alloy. If they're similar in size, they don't have to be the same size, but similar in size, then you're looking probably at a substitutional. So our next one says, which of the following would best represent an alloy of iron and carbon? Okay, so again, they don't give us the radii on this one, but we also need to know, and we're supposed to go and find out, that iron is in the middle of the transition elements, whereas carbon is 2 rows above it over in the nonmetals, and those are the small atoms. And so we're going to get a situation where the carbon is significantly less in radius, significantly smaller than the iron is. So something more like this situation. They wouldn't be very equal to each other. And there's only one size for each of these in an alloy. So we have to decide which of the following would be best. Because they're significantly different, we're looking for an interstitial alloy, right? And these top two pictures generally depict an interstitial alloy, don't they? But how do we tell the difference? It's because I'm supposed to know that iron is bigger than carbon. So iron would be the bigger atoms, whereas carbon would be the smaller atoms, not the other way around. So letter B would be our choice for that one. All right, you'll see some similarities with some of these questions. Take a moment and pause the video, similar question, and see if you can pick the correct structure for an alloy of boron and copper. And if you paid attention in our last example, you're looking for an interstitial alloy because boron is right next to carbon, and copper is down there near iron on the transition elements. So again, letter A would be the appropriate choice there. Again, lots of repetition. Which of the diagrams below represents an interstitial alloy? Easiest one of them all. They didn't even tell us which elements, but we're just looking for something with those interstitial spaces filled with a smaller atom. One more showing this one. And this time they give us a table with 4 different radii in it. This is part of a FRQ. Which of the diagrams below best represents zirconium and carbon? Again, we have zirconium, which is fairly large, carbon, which is fairly small. We have that, and so we're looking for an interstitial one, which is this one over here. And finally, those interstitial spaces, when they get filled, they make things a little bit harder. So we're going to use that on this particular question. We have 2 types of steel. Low carbon steel, not a lot of those low carbons in there. High carbon steel, we got more of them in there. This one's malleable and ductile, but this one is hard and brittle. So this is what the question is asking. Which of the following best explains why low carbon steel is more malleable than high carbon steel? Take a moment, pause the video, and see if you can guess the correct answer here. So low carbon steel has less carbon in it. So fewer carbon atoms allow for the iron atoms to move more easily, which makes it more malleable and ductile than something that has more carbon in it. And so that is our answer on that. So good job if you got that one. Every year in the FRQs, we see questions that ask us to draw particle models of things or diagrams, and we're getting more and more of that. So I'm going to show you an example of one of those, and then I'll show you how to draw an appropriate alloy diagram using inspiration from my truck axis over here. And then we'll have a pause the video moment so you can try one as well. White gold is an alloy of about 80% gold and 20% palladium. In the box below, draw a representation of this alloy. Your drawing should show enough atoms of each to represent the structure of the alloy. It should also be clear whether the alloy is substitutional or interstitial, and thankfully they gave us some numbers in this question, or we have the numbers in this question. Okay, so what should it look like? We'll get back to this in a second, but I know that my alloy that makes up my truck axis is mainly stainless steel, which is mainly iron with a little bit of carbon. And then I also have the addition of some manganese and chromium, but those are in small amounts. So my drawing has to represent all of that. Turns out this one here is actually a pretty complex alloy. It's actually both substitutional and interstitial. And this is what my drawing looks like. Okay, and take a look at it. So I've got mostly irons, and I made a little key over here. You'll probably be asked to do that, or you'll be given a key, like keep the white ones iron and keep the black ones manganese and stuff. So I drew a bunch of the atoms. I didn't just draw one of each, because that wouldn't be representative of what the actual alloy looks like. It's mostly iron, so I put them in there. And then I sprinkled in a couple of manganeses and a couple of chromiums. I don't know the exact percent, but I know it's smaller than the iron, so I threw those in there. And then I also, because there's carbons in there, and I know carbon is much smaller, by the way, these are most similar in size. They're almost right next to each other on the periodic table. So they're about the same size. And again, it doesn't have to be perfect. You don't have to be an artist on an AP exam. But the carbons I do know are very much smaller, and those are the things that help to make it a hard alloy by occupying some, maybe not all, of those interstitial spaces. So we have a bunch of atoms to show the relative proportions, and I've clearly shown that some are substituting and some are interstitial. So let's go back to our example problem. And knowing that you have only gold and palladium in here, and there are its sizes, take a minute and just go and sketch it in your notebook and see what kind of sketch you come up with. I'll show you mine and we'll compare notes. Back here in a second. Again, you don't have to be an artist on this, and in fact, I didn't even fill up the entire box, although I could have. I wanted to pay attention to this 80-20 situation. Because they gave me the percentages, I want my drawing to show those percentages. So I chose 10 atoms, which I thought was good, and I made 8 of them into golds, that would be 80%, and 2 of them, 20%, into palladiums. And I also noticed that gold and palladium are similar in size. So the palladiums are just going to substitute. They're not going to be in this little space in there at all. And I don't have any carbon to do that. So this is a pretty good drawing. They would look for labels on your atoms. Notice I just did the symbols this time and not the shadings. Pay attention to the question, see what they want you to do. And I used enough to show it, and I kept the ratio the same. So if you did that, that would be a good drawing. And I wish you luck on those when you take your AP exam. So hope you found this helpful. If you have questions, send it to me in the comments. And in the meantime, happy studying and have a great day.